This is CX1104 Linear Algebra for Computing, Chapter 8A.2. In this chapter, we'll continue with complex numbers in the exponential form, as well as the De Moivre's theorem. So let's begin. First, let's revise what the exponential form looks like. 5 to the exponent of 3 looks like this. 5 is the base, 3 is the exponent. 5 to the exponent of 3 means 5 multiplied by 5 multiplied by 5 3 times. So the exponent tells us how many times we are repeating this multiplication. And this number is 125. So 125 is the exponential form. 125 is what you get when you do 5 to the exponent of 3. So this is how we should say it. Or we can see it alternatively as the third power of 5. So what we are saying is that we are doing the third power of the base 5. Conventionally, you may see people saying it as 5 to the power of 3 to say the above. But this is not very accurate. And I asked Perplexity, why is this so? Perplexity is a large language model, and when I gave him the expression a to the power of n, the Perplexity answer was, oh, okay. It means in English, a and n are given, and this symbol a to the power of n is what I've just mentioned. But he also said a to the nth power, which is actually a much more accurate expression of what a to the power of n is. So 2 to the power of 3 or 2 to the third power. Okay, then when I ask him, hey, the word power also means the entire expression, right? This 5 to the exponent of 3 is 125. So 125 is actually the 5 to the exponent of 3. So he says, yes, I'm actually correct. A to the exponent of n is a more precise way to describe this term. Okay, a is called the base, n is the exponent, or sometimes also called the index. A to the power of n that means the entire expression is called the power. So he says that it is common usage to say a to the power of n, but it is not the technically precise way to say. Okay, so with that, we can now go to the next slide to discuss the complex exponential form. Now, Euler shows us that the complex number a plus jb, where a is cos theta and b is sine theta, can be expressed as this exponential form, where the base is e and the exponent is j theta. So it's complex exponential. The exponential in this exponential form is complex. So j theta is the exponent. So let's see all these terms here. Where is theta? Where is cos theta? Where is sine theta? So let's see the original representation that we are familiar with. Z is the complex number given by a real number a and an imaginary number ib. A plus ib. And this is the rectangular form, remember? And then we also remember that we could have written it as r angle theta, where r is the modulus and theta is the angle made with the real axis. So this is theta. The angle of z, where z is this phasor, this vector, and theta is the angle made with respect anti-clockwise to the real axis. Now, what about z, or what's r? R is equals to the modulus of z, the length of the vector. So in the right angle triangle, we use Pythagoras theorem. A is one side and B is the other side, and this is right angle. Then the hypotenuse is the length of this vector is square root of a squared plus b squared. So this is r equals to this. Now, once we have this, then if we use the Euler's formula to say that ej theta equals to cos theta plus j sine theta, then finally we can actually write the complex number in the third form, which is what's showing now, which is this, which is the modulus times cosine theta plus j sine theta, because isn't cosine theta plus j sine theta exactly what ej theta is by Euler's formula? So this is what we are trying to say here. We replace cos theta plus j sine theta with the complex exponential form ej theta. And now we have this basically 4 ways to write it, the complex number. And we'll realize that the complex exponential form is a very nice way to write complex numbers because it allows us to manipulate it very easily. Okay, in the next few slides, I'll then go through how to derive ej theta is equal to cos theta plus j sine theta. Thank you.